Welcome to Lecture 2.5, the transpose of a linear map. Every undergraduate linear algebra student learns about the transpose of a matrix, formed by flipping it across its main diagonal. But what does this really represent in terms of the actual linear map itself? The transpose of a matrix is what results from swapping rows with columns. In our setting, in this class, we like to think about vectors in our space X as column vectors and dual vectors in the dual space as row vectors. So what does that mean about swapping rows with columns? Think about that. Indeed, the transpose is a more general concept than just an operation on matrices. Given a linear map, T, from X to U, its transpose is a certain induced linear map. We'll call it T prime because it goes between the dual spaces in the reverse order. So it goes from U prime to X prime. In the next lecture, we will learn how to encode linear maps with matrices. When we do this, the matrix of the transpose map will simply be the transpose of the matrix. In this lecture, we will introduce the transpose of a linear map and study some of its basic properties. If you haven't already, I strongly recommend that you watch the lecture directly before this, that is lecture 2.4, the 4 subspaces. It may be a little bit out of place because we haven't seen in this class how to define a matrix from a linear map, and the previous lecture is all about matrices and certain subspaces, namely the column space, the row space, the null space, and the left null space. And indeed, that lecture is meant to be a review of some of the big ideas from undergraduate linear algebra, which is a prereq for this course, and it puts them together in sort of a unifying framework, which I think is going to be very useful for this lecture and the next. And I say that because it'll give some context. So when you see things like what will come up later in this lecture, the annihilator of the range of T is the null space of the transpose, you'll have something more concrete to compare it to, involving row space and column space and the null spaces. Okay, so let's get started. Throughout, T will be a linear map from X to U, and L will be in the dual space of U. The composition will denote M, which is L of T, is a linear map from X to K. So remember, T goes from X to U, and L goes from U to K. So L of T is in the dual space of X. Since T is fixed, this defines a linear map called the transpose of T, denoted T prime, and it goes from U prime to X prime, which sends L to M. That is L to L of T. Here is a diagram that I think really illustrates the idea of a transpose quite well. So T is a linear map from X to U that is fixed throughout, and then for any L that I put right here, in other words, for any dual vector of U, we canonically get a dual vector of X, a map from X to K, which is just done by precomposing with T. Now, throughout this lecture, I recommend using scalar product notation. So instead of writing M of X, which is just L of T of X, we can write that as M comma X, which is L comma Tx. I'll still say M of X and L of Tx, but as we'll see shortly, it helps to write it in this form. Let me show you why. The transpose of T is the unique linear map T prime that satisfies this M up here being T prime of L. Now let me pause to explain what I just said in an unfortunate bit of notation. So by T prime L, I mean T prime of L. So L is the input. Sort of like how I might write Tx, short for T of x. Now I say unfortunately because up here I wrote LT, and I actually think I said L of t, because this is literally the composition of two maps. Now if I have two linear maps and I say A of B, that really means that, say, I am doing B first and then I'm doing A. But if I say B of x, then I usually mean B is a linear map and I'm inputting x. So I say A of B for composition and I say B of x for inputting x to B, and I write in the same way too. So AB and BX. So you have to just be a little bit aware from the context that this is different from this. And unfortunately, we say the same thing. Okay, let's go back to this key property. So the transpose T prime is the map such that T prime of L equals M. Now let's look at what I highlighted up here in red, and let's take this T prime L and plug it in for M. And if we do that, we get this statement. T prime L of x equals L of Tx for all vectors x and all covectors of u, L. Now, what you should notice about this is that it obviously does not make any sense to take this t and put it on the left-hand side. So we can't just write TL of x. That doesn't make sense, that they live in different spaces. But we can put a prime here. So if we want to stick the t on the left-hand side, the transpose is the map that allows us to do it. Now I want to remind you of that caveat that I mentioned earlier. I'm writing LT for L of t, the composition t then L, but t prime L does not mean t prime then L, in the same way that Tx does not mean T prime, or does not mean T then X. So this is short for T prime of L, like this. Here are three basic properties of transposes that I will leave for the homework. And I'll also leave a statement whenever meaningful, vague intentionally. So it should be clear that if T and R have different domains, like one of these is a 5-dimensional space and one is a 6-dimensional space, then you can't just add them up. And actually, even if the domains are the same dimension but they're different spaces, you can't add them up either. Okay, so the first one says that the transpose of ST is equal to T transpose S transpose. The second one says the transpose of the sum is the sum of the transposes. And the third one says that the transpose of the inverse is the inverse of the transpose. For all of these, I strongly recommend that you use a diagram like this, if nothing else, just to help you visualize it and clarify things and see which way the map should go. And let me show you what this might look like for this first one. I'll get you started. So the first one says the transpose of ST. So that really means, again, we're reading right to left, do T, then do S. So, suppose T is as before, and let's say that S goes from U to V, then the composition of this is ST. So it's S of T. I'll write it like that. So now what's the transpose? The transpose is the map ST transpose that goes from V, from the dual space of V to the dual space of X. So let's see, M L, what have I not used? Let me use put an N here. So the transpose takes this map N and it sends it to, so it sends N to the composition of S of T and then N. So we're going to be careful that we write these in the right order. So N is last, and then it's S of T. And now, what is this? Actually, I think I'm missing a. This is S here. So what is this? This is doing T, then S, then N. All right. So let me write that N, S, T. So it's the map that sends N to doing T, then doing S, then doing N. So it really sends this N to this M up here, which is NST. Now, this map can be broken up into two steps. You can first send N to this L, and L, then send L to this M. So in other words, where do I want to put this? So N gets sent to what is L here? L is Sn, so N gets sent to Ns. So I'm just precomposing with S, and then I'm precomposing with T. So this is how you should think about the transpose. The transpose of S just precomposes with S, and the transpose of T just precomposes with T. And of course, all this is saying is that precomposing with S and precomposing with T is just precomposing with S, T. So I've basically done the proof here, but I will let you write it out nice and formally on your own time. Let's continue with example, namely systems of equations, because we know that matrices will arise from that, and we are familiar with the transpose of a matrix, and somehow these things are the same. So in this lecture only, I will use a capital N and a capital M. That's because I have used the lowercase m. Remember, I've used m as LT. So I don't want to reuse that for this. Okay, so suppose that Tx equals U, and again, Ui is a linear combination of the xi's. So I'll write this. Here's what this looks like in terms of commutative diagrams. So T goes from Rn to Rm, and for any scalar function from Rm to K, the transpose sends this L, it just precomposes with T. Okay, so here's an element-wise picture of that. Now, by definition, for some scalars, L1 up to Lm, the scalar product L of U is, well, we know it's, think of it like a dot product. It's just the sum of Li Ui. Now, I'm highlighting this Ui in red because what is Ui? Ui is this thing up here. So we can just stick that in for Ui. And if we do, we get this creature. And now, this Li, you can't stop me from moving it inside the sum here to get this. And now this is a double sum. So I can swap the order of the sums because these are finite, and stick the U, the Li out here. And now from here, I can regroup the Li and the Tij's and write this as this instead of a sum of m terms, a sum of n terms, mj, xj. Now I know I went through this quickly. I will unravel it on the next slide. I just wanted to give you a high-level overview first, And of course, anytime you see things like double subscripts, double sums, it is hard to visualize exactly what is going on. So this is an algebraic overview, and it gives us a formula for what this m actually is in terms of these coefficients. Later, we will see something that I've said before, that if we express t in matrix form, the transpose is what we get by just swapping rows and columns. Now, as promised, I want to return to this double sum algebra jargon that I wrote down and dissect it so we can really understand what's going on. Let me first emphasize what's in red here. So the system of equations is ui is the sum j equals 1 to n of tij xj. So what that really means is that u1 is t11 x1 plus t12 x2 plus t1, make sure I have my, so n, my indices right, t1n times xn. Similarly, u2 is t21 x1 plus t22 x2 plus t2n xn. And um is tm1 x1 plus tm2 x2. I know it's tedious to do this, but I think it's worth it, and I think you'll agree with me when we finish this. tmn xn. Okay, so now I'm going to pause to copy paste this, and you'll see why shortly. Okay, and voila, like magic. Okay, now this is the system of equations up here, and this linear scalar function, L of u, should really think about as like a row vector L1 up to Lm times u1 up to um. So that is like what if I put L1 times u1 plus L2 times u2 up to Lm times um. If I do that and I add this up, then what I get here is L1 u1 plus L2 u2 plus Lm um right here. Now let me put parentheses around here so you can really see what we're doing. I mean, you can think about this instead as L1 times this linear combination plus L2 times this linear combination and Lm times this linear combination. So let me just emphasize here that these are really like rows. So we are taking a linear combination of rows. And what we're going to end up here is take a different linear combination of columns to get the same thing. So bear with me. So I'm going to retake this system and put it down here, and I'm going to stick now stick L1s so everywhere. So L1s are going to be in here. L2s are going to be in here. And then LMs are going to be everywhere in this last row. Okay, and now what I want you to do is I want you to look at this not by rows, but by columns, like this. Now it's, and what we're going to do, instead of adding up a linear combination of these rows, we'll add up a linear combination of these columns. Now it's a little bit weird to do. I still like to, we write things left to right. So I'm going to rewrite this system in its so-called transpose form. So I'm going to write these these columns as rows. So in terms of undergraduate algebra, I'm going to actually take like the transpose of this matrix. So this first column is going to be, so this, in other words, this column right here, I'm going to write as a row, and make sure that I do this right. It is going to be L1 T11 X1 plus L2 T21 X1 plus all the way up to LM TM1 X1. And then the next column becomes the next row, which is L1 T 1 2, sorry about that, X2 plus L2 T22 X2 plus LM TM2 X2 all the way up to the last one, which is L1 T1 N XN plus L2 T2N XN plus LM TMN XN. Okay, so these columns have now become these rows, and let me use that same color again to emphasize that. And now what I want you to notice is I sort of want to undo this process here. So here here you can factor out these L's like this, and so in other words, L1 is a constant, or L1 appeared in every term in this first row, L2 appears every term here, and so forth. And look what happens here. Now we have this X1 that appears in every term in this first row, this X2 that appears in every term in the second row, and so forth. So I can really write this. So now I'm going to factor out my X1 times what? So times L1 T11 plus L2 T21 plus LM TM1. And then the next one, it's LX2 times L1 times T12 plus L2 times T22 plus LM times TM2, and so forth. And then all the way down to, I'm going to factor out an XN, because that appears in all of these. So I got to be careful that I'm keeping my capital N there, capital XN, times L1 T1N plus L2 T2N plus L M T M N. Okay, and now I am almost back to where I started with. What we did is this UI, so this linear combination, we called UI. So UI is equal to this. So basically U1 is equal to this, U2 is equal to this, and so forth. And now this linear combination, we want to call this MI. So this is going to be X1 M1. This is X2 M2. And this is XN MN. And that is exactly what we have right here. So now, if we add this thing up, we get X1 M1 plus X2 M2 plus XN MN, and compare this thing here, which is what we have up here, to this thing here, what we started with, which we went through the steps, showed it was the same, which is these things right here. And I guess I could have written this. I could have written this now as m dot x. Now, in summary, this is pretty messy. There's double subscripts. So just look at the high level. We are taking linear combinations of rows here. If we do that and we move these coefficients inside, we can, instead of looking by rows, we can look by columns. And then now it's still easier to write that by writing these columns as rows, but taking the matrix transpose, as we know from our early days of linear algebra. And that gives us a different linear combination. And that's what this is here. Now, the one thing I want to leave you with is thinking of this in terms of matrices and columns and rows. So this grid here of numbers, just the TIs, I want you to think of as the matrix T, something like this. And then with the xi's here, so this is just T times X. And then when I take linear combinations of the rows, what I'm really doing is I'm multiplying by L, that is the row vector. Let me call that L transpose, just to emphasize that it's a row vector on the left. So this system here, as I've drawn it, is really L times Tx. So you put parentheses like that. That's what this is. What we've ended up here is we've basically just put parentheses differently. We've put parentheses here. So if we put parentheses there, then this whole term, LT, is just this thing in red, and X, so the dot product. In other words, this is an n-dimensional vector. The dot product of that with an n-dimensional vector is this sum right here. But if we put our original blue parentheses here, right here, now we have an m-dimensional vector, and we take the dot product of that with this m-dimensional vector. And that's all this is. It is literally just taking L, T, X. One of these ways is saying, hey, look, you can put parentheses here. And the other way is saying, you could take L, T, X, and you could put parentheses there instead. Both of these you can think of as dot products, a row times a column. These are m-dimensional vectors. These are n-dimensional row times an n-dimensional column. That's it. It's basically just not anything harder than the associativity property, at least with systems of equations. And that's what the idea of the transposes is basically generalizing. Let's now prove a few basic results about the transpose. But first of all, I'll leave this as verification, as a simple exercise, that if we canonically identify the double duals of x and u with the original spaces x and u, then the transpose of the transpose is just T itself. Next up, a simple result that says the annihilator of the range of T is the null space of its transpose. This is the thing you look at and you think about and you wrap your head around what it's really saying. And with that diagram of x goes to u and k, this thing, you could probably do it. And I recommend looking at this diagram and thinking about it and convincing yourself why this is true. But I also recommend that you specialize to that case of matrices that we talked about in the previous lecture, and the four subspaces, and really understand why this is true in that setting. So here you have T is a linear map from x to u. We can think of u as like the direct sum of the range of T and the left null space. This is why you need to watch that lecture right before this one. And then x you can think of as the direct sum as of the row space, the range of the transpose, and the null space of T. So what this is really saying is that the vectors that are perpendicular to this is the left null space. And we saw why that's true in the previous lecture. Of course, this doesn't quite apply because here we're talking about dual spaces and annihilators, and here we just have, this is like Rn and Rm. But it still helps us understand why this should be true. So let's prove this, and I claim that the proof is actually very straightforward. We just use the definition. So the annihilator of the range, by definition, so where does this live? This lives in the dual, because the range lives in U. And so the annihilator lives in the dual of U. So this is all linear functions, linear scalar functions, or dual functions, dual vectors, such that, now what does it mean to annihilate everything in the range? That means that L of U equals 0 for all U in the range. That's just the definition of the annihilator of this subspace. Now, to be in the range, that means it has the form Tx. So let's just write that down. This is equal to a set of all linear functions in the dual, so that L of Tx equals 0 for all x in X. Okay, now this is really why it's so important to use that scalar product notation. Here's what you want to do. Take that T and move it over to the left-hand side. Make it a T prime. If you do that, it's a set of all L in U prime such that T prime L of X equals 0 for all x in X. And that's exactly what it means for this guy here to be the 0 function. And that's exactly what it means. And so, well, so if T prime is this linear map, if applied to L, then that's exactly what it means to be in the null space of T prime. So this, by definition, is the null space of T prime. It's a set of all L's for which this is the 0 function. So this really just fell out on our lap. Now this is why, hopefully I've impressed upon you, why it's so important to use the scalar product notation. I mean, imagine doing this without that. This first one would be, you'd have an L of U equals 0. And then this next one here, this is L of T of X. And then this last, again, without that scalar product notation, you have a formula for T prime, but it's not as visually clear as just knocking it over the left-hand side. Okay, so what's next? What do you think comes here? Well, if you look at this picture, or I guess this result, there's two canonical things that you can do. Let's look at this right here, and one thing you can do is apply perp to both sides. And if you apply the perp to both sides, remember that double perp gets you back to where you started. So if you take this thing and you apply, so you get RT perp perp equals N T prime perp, which is RT. So you get that the range of T is the annihilator of the null space of the transpose. That's a mouthful to say or to think about. So what is the annihilator of the null space of the transpose? And why is it equal to the range? Well, it falls right out from just applying perp to this. Of course, the other thing you could do is conclude the same thing about the transpose map. So if you apply this to the transpose map, going backwards, now you get, what do you get? You get that the range of the annihilator of the range of the transpose map is equal to the null space of the transpose of the transpose. which is just the null space right here. So you get this as a corollary, and you also get this as a corollary. Now I didn't think to actually write down both of these, so I just wrote down one of them typed up, but I basically said both of them. You apply perp to both sides, and you get the following corollary. The range of T is the annihilator of the null space of the transpose, i.e. just this. Now we come to a pretty significant theorem. It says for any linear mapping T, the dimension of its range and the dimension of the range of its transpose are the same. This is the abstract version of the fundamental theorem that I told you for matrix analysis, that the row space and the column space of any matrix have the same dimension. This is a much more general statement. And we actually have the tools to prove it pretty easily. We just have to put them together. So let me show you how to do that. So we just proved, the previous slide, that the annihilator of the range of T is equal to the null space of the transpose. Now we have a fundamental result about annihilators, and that is the dimension of the annihilator of any subspace plus the dimension of the space adds up to the dimension of the space it lives in. So remember that the dimension, so let me use this space, of the annihilator plus the dimension of the range itself equals the dimension of the space it lives in. Now where does this live? This, the range lives in U. Okay, now this other thing, the null space of the transpose. We have a fundamental result about null space of a linear map, and that's the rank nullity theorem. This says that the dimension of the null space of the transpose plus the dimension of the range of the transpose is the dimension of, now what's the domain of the transpose? The transpose goes from U prime to X prime, so that's the dimension of U prime. Now we know that these two things are equal. The dimension of any finite dimensional space is equal to the dimension of its dual. And of course, these two things are equal because they are not just equal for dimensions, but they are the same space. So these two are equal, these two are equal, and therefore that means that these two are equal. So how do I say that? These must be equal. So I'm not going to write this out in a sentence form, but you get the basic idea from these two basic statements that we've proven. Well, if these are equal and these are equal, these must be equal as well. And that's it. We got a corollary of this is that if we have a linear map T and X and U have the same dimensions, then the null spaces have the same dimensions as well. So the four subspace picture of that is that if this is X and this is U, then remember this is the range of T, this is the left null space, this is the range of the transpose, and this is the null space. So what we showed in the previous result is that these have the same dimension, and so this is dimension, let's call this R. This is, and this here is dimension of U minus R. This is dimension R, and this is dimension of X minus R. So once again, I guess I don't think I even need really to write this. I'll let you finish out a formal proof if you want, but we know that, well, sure, why not? The dimension of the null space of T is the dimension of X minus the dimension of the range of T prime, and the dimension of the null space of the transpose is just this difference. It's the dimension of U minus the dimension minus the rank, or R, which is the dimension of the range of T. And if these things are equal and these things are equal, then these must be equal as well. So I'll say that. So this is assumption. These are equal, and this is by theorem 2.11. Okay, so that's all I want to say about transposes. And next up, I will show you how to construct the matrix at last of any linear map between finite dimensional vector spaces. Stay with us.